Morning, class. Hope you can see everything well. So I'm going to give you the answer to the problem. Some of you already got the answer. 3 people got it. Sukdeep, Elbron, and Ramela. Congratulations. You get your bonus. So that question is closed now, and I'll give you the solution. So just to be clear, this class can be used both by the grade 11U and 12C because it's the same content essentially. So the question I asked yesterday was 35 milliliters of butane with a density of 0.6 grams per centimeter cubed is burned. How much oxygen is needed? So clearly it's a combustion reaction. You're burning butane. So when you solve any of these types of problems, this is a stoichiometry problem. But before you can solve the stoichiometry, you've got to balance the equation. So you've got a combustion equation. So it's combustion of butane. By the way, I recommend you, if you're going to watch me, do so on a television set. The phone is not going to do justice to the content. We had a problem yesterday that somebody thought 30, Elbron it was, he thought 35 was actually 350 because you couldn't see the decimal point. So this is a small format, so it's best to use a television to give you the maximum detail. So butane is C4H10. You need oxygen to support combustion, and the products of complete combustion are carbon dioxide and water. Now, when you balance a combustion equation, I taught you the trick already. You balance alphabetically. You start with C, then you do work on the H, and then the last thing you balance is the O. C, H, O, alphabetical order. So there's 4 carbon atoms in butane, so you have to have 4 carbon atoms in the form of CO2. All the carbon that was present in the butane has now been turned into carbon dioxide in a complete combustion reaction. There's 10 hydrogens, so you're going to have to put 5 waters because that's going to give you the 10 hydrogens. The 10 hydrogens that were formerly in the form of butane have now turned into the 10 hydrogens that are present in water. Once you've balanced the carbon and the hydrogen, you then proceed to balance the oxygens. But then you go to the other side of the equation and count how many oxygens appear. So 4 times 2 gives you 8 over here, plus 5 over here. So there's 13 oxygens to balance the equation. So if we put a 13 over here, it's going to give us twice as many oxygens as we really want. So we're going to say 13 over 2. But as most of you know already, I don't like to have fractions in my balanced equation. So I'm just going to double everything. I'm going to double all the numbers. It's going to get rid of that fraction. So a 2 is going to appear here. This is going to turn into 13. That's going to turn into an 8. And that's going to be a 10. So now you have a balanced equation using only integer values. And the question asks 35 milliliters of butane. So you have 35 milliliters. And the conversion factor between centimeters cubed and milliliters is 1 to 1 in things, in any liquid. Typically, you'll see milliliters used for measuring liquids, centimeters cubed for measuring solids, but it's not a hard and fast rule. The two are interchangeable. There's 1 centimeter cubed for every milliliter. So that allows you to cancel milliliters. You have 35 centimeters cubed of butane. The density, we're told, is 0.6. Density is equal to mass over volume. For those of you who are not familiar with this funny symbol, it's the letter rho. It's a Greek letter. It's the letter that you use for describing density. So scientists like to assign different letters for different variables. For example, you've heard of alpha radiation, beta radiation, gamma radiation. 3 different Greek letters assigned to different types of radiation. So when you're talking about density, the official letter you use is rho. That's the Greek letter rho. You don't have to do it if you don't want. You could use just the letter D. It doesn't matter. It's not that important. But we're going to solve for the mass of butane that is present. So density times volume is equal to mass. And we're told the density is 0.6. So we're going to say 0.6 grams per centimeter cubed. And we have 35 centimeters cubed of butane. That's going to allow us to cancel centimeters cubed. Our answer is going to be in grams. So we have 21.0 grams of butane. I'll just give you 30 seconds to copy that in case you're falling behind. And then I'll give you the rest of the answer since our board is minuscule. How many of you are online? There's 3 people online. Wow. Well, congratulations for caring. But this is your education, folks, so you got to take charge of that part. Okay, so I'm going to make some room now. We have 21 grams of butane. And if you recall the stoichiometry between, we're asked how much oxygen is necessary to burn those 21 grams of butane. The stoichiometry of the reaction is the stoichiometry of the reaction is 13 to 2. That means 13 moles of oxygen is needed to burn 2 moles of butane. But before we could even solve it, remember the scheme I taught you for solving these type of problems. You start off with grams of substance and you go to moles. And then from moles of the first substance, you go to moles of the second substance. And then finally at the end, you go back to the grams of whatever other substance they ask you to find out. In this case, we're starting with butane. You divide by the molar mass of butane to find the moles of butane, right here. And then you go over the stoichiometry, which is going to be 13 over 2 in this particular case, to find out moles of oxygen. And then you multiply at the end by the molar mass of oxygen to get the grams of oxygen. So that's the scheme we're going to follow. So we start off with 21 grams of butane, C4H10, divided by the molar mass of butane, which is composed of 4 carbon atoms weighing 12.011 each, plus 10 hydrogens weighing 1.00794 grams each per mole. So that works out to 21.0 grams of butane divided by the molar mass of butane, which is 58.1234. It almost seems contrived, but that's the actual mass of butane. So that gives you, so we're here now, we're dividing by molar mass. That's the molar mass of butane, and we're going to get this quantity, which is moles of butane. The answer turns out to be 0.3613 0.00268 moles of butane. Then, to go from here to here, you remember the balanced equation was 13 moles of oxygen is necessary for every 2 moles of butane. So we're going to do that right here. We're going to say times 13 moles O2 for every 2 moles of butane, C4H10. So what you get now is you're gonna be over here, is you get that you require 2.384, sorry, 2.348, 45174 moles of oxygen. And then what we do is multiply by the molar mass of oxygen to obtain the grams of oxygen. Remember, oxygen is diatomic, so it's going to be 2 times 15.394 grams per mole. Final answer you're going to get is 75.1476376. That's what I got in my calculator readout. Of course, you only have 3 significant, actually no, you get 2 significant figures because I used 0.6. So officially, your answer should be 80 because of only 2 sig figs. Let's pretend I said 0.60, making it 3 sig figs. So we're going to get an answer of 75.1 grams of oxygen is necessary to burn 35 milliliters of butane, according to the parameters I've established here. But of course, butane does not necessarily have a density of 0.6. I didn't actually look up the density of butane, I just made it up. But it's close to that. Most hydrocarbons are in the neighborhood of 0.6 to 0.8 in terms of density. Which is why, incidentally, if you get any water in your gas tank, where's the water going to go? Water has a density of 1, gasoline has a density of around 0.7, so the water is going to go straight to the bottom of your gas tank. And that's why if you have water contamination in your gas tank, the first thing that happens is it blocks it goes into your fuel line, and because your fuel line is very thin, it freezes very quickly. So in provinces in Canada where the temperature drops to say minus 20 or 30, you can get what's called vapor lock. So the moisture that's in your gas tank can condense, fall into the gas, and then go to the bottom of the tank. Hey, Mama, we have another student. Look at him. Say hi, Mama. There he is. You see him? Okay, so the next question I want to do is number 350 from your textbook, from chapter 3, of course. I'm just going to do 4 questions today. We're going to do a little mock test just to warm you up, and then it might give you the chance to ask some questions. If everything works out, if the internet doesn't go dark in the next few days, Mama, you shouldn't be biting that wire. You're gonna make the phone fall down. No, don't do that. So my plan is to go up to chapter 4 if you guys are into it. Of course, you don't have a copy of chapter 4 as I recall. So anyway, we'll make it work. You'll still get something out of it. Okay, I'm gonna have to disconnect the phone because Mama is biting my line, my charger line. Just gonna make it fall. You're being naughty. All right. So the next question is 350. The question is, determine the empirical and molecular formulas of each of the following substances. Ibuprofen, a headache remedy, contains 75.69% carbon, 8.8% hydrogen, and 15.51% oxygen by mass, and has a molar mass about 206 grams. This is an empirical formula determination. Empirical formula determinations were used in early chemistry to find out the composition of an unknown substance. And the way they would do it is they would burn the substance and collect the carbon dioxide and the water that would form during the complete combustion process into pre-weighed vessels. And then when you add CO2 to a substance that exclusively absorbs carbon dioxide, the increase in weight allows you to determine how much carbon was in the original sample that was burned. So it's called combustion analysis. Your book, chapter 3, has a description of all of that. So to solve these types of problems, what you do is assume that you have 100 grams of the sample. Now, if you assume that you have a 100-gram sample, you're going to, it'll make it easier for you to do the calculation. All you have to do then is turn your percentages into gram amounts. So the compound is 75.69% carbon. So if you have a 100-gram sample, that means you have 75.69 grams of carbon in the sample. Likewise, you're going to have 8.8 grams of hydrogen and 15.51 grams of oxygen. Divide each one of these quantities by the molar mass of the substance, of the element. Oxygen is 15.394 grams per mole, and you're going to get the amount of moles of each of the elements involved in that particular sample that weighs 100 grams. So what you get is, in this case, I'm just going to go to 4 decimal places. That should be enough for our purposes. 6.3017, 8.7307, and 0.9691. Now what you do is you divide by the smallest number of those 3. The smallest number in that series is this one. And that has the effect of creating, if you're lucky, you're going to get some whole number ratios. In our case, it doesn't give you whole numbers. You get 6.5, 9, and 1. But what does that tell you right away? You can't have 6.5 carbon atoms. So what you do is you multiply these numbers by the lowest integer value that will give you whole numbers. And in this case, if you multiply everything in here by 2, you're going to get C13, H18, O2. And that is the empirical formula of ibuprofen. Let's find out if it matches the molecular mass that they give in the book. In the book they say that the actual molecule ibuprofen has a molar mass of 206. So let's try that now. You're going to, so we're finding out the empirical formula weight. So 13 times 12.011, which is the molar mass of carbon, plus 18 times 1.00794, which is the molar mass of hydrogen, plus 2 times the molar mass of oxygen, yields an answer of 206.28 grams per mole. Well, the molar mass is in fact 206. Therefore, we could say molar mass equals the empirical formula weight. Therefore, it is the same formula. All right. The molecular formula and the empirical formula are identical. It may sometimes happen that it's not identical, but whatever multiple of that it should be. So suppose you instead of this, we had been told that the molecular weight was 412. 412 is twice 206, so you would know that the actual formula, the molecular mass, is twice the empirical formula. So you would then simply multiply this thing by 2, and it would mean that the actual formula was C26 H36O4. Okay? That's an empirical formula problem. The next one is it's a doozy. It's a long one, but it's worth doing because it uses all the skills you need to know for chapter 3. If you can do number 359, which we're about to do, then you basically know the chapter sufficiently well to do well in any test I would give you. So we're going to try 359. I'll read you the question first, and then I'll start doing it. I'm not going to waste any time waiting for you to do it. Now, if you watch this video at a later time, you can pause it and then try to solve it. It shouldn't take you more than about 15 minutes to solve the problem. and test yourselves. So see how well you're doing. I hope some of you are at least trying to do the 80 question assignment that I gave you, because it's going to pay off. I promise you, if you do it, it's going to pay off. And I'm now reworking the solutions. You see where I rewrote the notes in case you're interested. So this is my old chapter 3, full of mistakes, because it was the first time I did it. Now this is the brand new chapter 3, and the notes are updated. There's more explanations, and I worked out all the answers. So you're gonna have a hard time finding mistakes in here, is my prediction. And if you do, I'll reward you the same way I always do if you find my mistakes, because then you can improve the experience for future generations of students, at least until I retire anyway. So let's read the question. Number 359 says, several brands of antacids use aluminum hydroxide. By the way, I wouldn't recommend putting aluminum in your body. It's not good for you. Yeah, see, Mamo agrees. So several brands of antacids use aluminum hydroxide to react with stomach acid, which contains primarily hydrochloric acid. So they give you the balanced equation for the neutralization of the hydrochloric acid in your stomach by the aluminum chloride. I'll write that in a minute. So there's 4 parts of the question. Balance the equation. B, calculate the number of grams of hydrochloric acid that can react with 0.5 grams of aluminum hydroxide. C, calculate the number of grams of aluminum chloride and the number of grams of water formed when 0.5 grams of aluminum hydroxide reacts. And D, show that your calculations in part B and C are consistent with the law of conservation of mass. The law of conservation of mass, I'll remind you, tells you that whatever reactants were at the beginning of the reaction, they're all still there in the products. Now, if you think of a fire, if you burn a 50-pound log, you're not going to get 50 pounds of ash. So it might not look like the law of conservation of mass. It makes sense. It may seem like a contradiction, but the reality is that the 50-pound log is combining with oxygen in the air. It's producing carbon dioxide. It's producing soot. It's producing the evaporation of water in the log. It's also producing water from the combustion of the lignin in the wood and the cellulose and whatever else is present. But if you were able to somehow gather all the products of the reaction and weigh them, you would find that they weigh exactly as much as the log plus the amount of oxygen that was burned. So that's what the law of conservation of mass says. Basically, anytime you have a chemical reaction, material isn't just disappearing, it's only rearranging. Everything that is reacting chemically is rearranging into different substances, but everything is still there. So in theory, the proteins that make up the muscles in your left arm, if you go back in time far enough, at some point they may have been the arm of a T-Rex. Or the same molecules that were in the muscles of the arm of the T-Rex are now in the bicep. Some of the same carbon atoms that were on the Earth 65 million years ago are still present on the Earth, and they're being recycled continuously. So there's constant recycling of atoms, and the law of conservation of mass is, that's what it's basically saying. Okay, let's start by copying the equation. This is from 359. In Brown. So it's from your textbook, Brown and Others, 10th edition. It's got a white cover. It's this textbook. I'll show you. I got to give credit where credit is due. I'm using this textbook, and I'm on page 115 right now, which is chapter 3. No, sorry, page 114. So the equation is this: aluminum hydroxide, which is a solid, is reacting with hydrochloric acid, which is aqueous. And once it reacts in your stomach, you're going to form aluminum chloride and water. So that's not a balanced equation. You got to have the same number of elements on the left as you do on the right. So you have one aluminum, one chlorine, three chlorines. So there's an imbalance. So you're going to have to put a 3 over here for sure, at least. So now you can have the 3 chlorines on the left, 3 chlorines on the right, 3 hydrogens plus 3 hydrogens, because 3 times the hydrogens inside that bracket means there's 6 hydrogens on the left. So you've got to have 6 hydrogens on the right. 3 times 2 gives you 6. So the hydrogens balance. And let's just double check everything again. 1 aluminum, 1 aluminum. 3 hydroxides plus 3 hydrogens. You can add those up to give you 3 waters. And there's your 3 waters. And then 3 chlorines, 3 chlorines. It's balanced. Now, again, we're going to use the same scheme of going from grams of substance to moles of substance, and from moles of one substance to moles of another substance, and then back to grams of the other substance. In this case, we're starting with aluminum hydroxide, and we want to end up with grams of hydrochloric acid neutralized. So we have to follow the same process. It's always the same idea. It's always the same. The whole chapter is this algorithm. You might be starting here, you might be starting here, you could be starting here and going this way. So all the permutations are possible. You could start at any point on the diagram and end up at any other point on the diagram. You simply have to know what the steps are to get through each one of the different parts. Just follow the sequence. So we're going to start by finding out how many moles of aluminum hydroxide we have. We're told in the question that there's 0.500 grams of aluminum hydroxide. So we're going to divide by the molar mass of aluminum, which is 26.98154, and 3 times the mass of oxygen, which is 15.394, and 3 times the mass of hydrogen, which is 1.00794 grams per mole. Divide this by that. Well, let's find out what this totals up to. It's 0.500 grams divided by 78.00356 grams per mole. So grams divided grams per mole, which is the molar mass, means you're going to have 6.4099 6385, sorry, times 10 to the minus 3 moles of aluminum hydroxide. Stoichiometry is 3 to 1. See, 3 moles of hydrochloric acid is needed for every 1 mole of aluminum hydroxide. So what we're going to say is times 3 moles of hydrochloric acid appearing for every 1 mole of aluminum hydroxide that is used, and that's going to equal, and I have to write it over here because there's no room on this minuscule board. What you're going to get is not 1.92298916 times 10 to the minus 2 moles of HCl. Now you're going to multiply by the molar mass of hydrochloric acid to find out grams of hydrochloric acid. And where am I going to do that? So I have the moles of hydrochloric acid. I'm going to have to erase that. Give you a few seconds to write it. So we're at the point where on this little diagram where it goes grams to moles to moles to grams, we're here now. So now we're going to go from moles of hydrochloric acid to grams of hydrochloric acid. I'm going to leave the equation on. I'm just going to erase the other parts. So we have 1.922 times 10 to the minus 2 moles of hydrochloric acid times the molar mass of hydrogen, which is 1.00794, plus the molar mass of chlorine, which is 35.4527 grams per mole, which is actually working out to was it hydrochloric acid? Yeah, which is working out to 36.46064 grams per mole. That's the molar mass of HCl. So you take this number, multiply it by that number. This is the moles of hydrochloric acid. This is the molar mass of hydrochloric acid. Moles will cancel. And your answer will be in grams. So what you get is 0.7011 34155 grams of hydrochloric acid. You're only allowed 3 sig figs, so you're going to write 0.701 grams of HCl. That's part B done. You know what, guys? If you're when you have a moment, just put your name on in the comments so I just know who attended. And part C, it asks you how many grams of aluminum chloride is formed. All right, it's a similar type of question, except now the stoichiometry is 1 to 1. Before it was 1 to 3, now it's 1 to 1. You see, you can do this calculation for any other substance. You can compare any substance in the equation with any other substance in the equation, and by knowing the balanced equation, and which is the stoichiometry of the reaction, what you get, hi Stella, what you get is the prediction of what's going to be produced, or how much you need for the reaction to work. Hi Ramella. I'm seeing your names pop up as you answer. So it's a 1 to 1 stoichiometry. And we already did the calculation for the aluminum chloride. We already know how much aluminum chloride moles there are. It's 6.4099 times 10 to the minus 3. So we just restart the calculation. We already know the number. Don't go bothering to recalculate it. It's 6.4099 6385 times 10 to the minus 3 moles of aluminum chloride is what we're starting off with. And we're getting the same number of moles of aluminum chloride as we did of aluminum hydroxide because of that 1 to 1 stoichiometry. So whatever moles of aluminum hydroxide, you got the same number of moles of aluminum chloride. So now all we're going to do is multiply by the molar mass of aluminum chloride, which is constituted of aluminum, 26.98154, plus 3 times chlorine, 35.4527 grams per mole. So that's the molar mass of 133.33. That's not your answer yet. That's just the molar mass. That's what this bracket equals. Actually, I'm going to write it up here so you don't get confused. So the contents bracket is 133.33964 grams per mole. Of course, you realize if you make a mistake in calculating the molar mass of your substance, everything after that point is going to be wrong, which is very frustrating because you're going to get wrong answers. So you just got to be careful as you're doing your calculation. So now we're going to multiply this by that, and what you get is 0.854702272 grams of aluminum chloride is produced, and you're going to report it to 3 sig fig, so you're going to say 0.855 grams of aluminum chloride. Okay. The last question where they ask you to do some stoichiometric calculations is the second part of C, which says calculate the number of grams of AlCl3 and the number of grams of H2O. So now we're going to find out the grams of H2O. Again, same balanced equation, but now you'll notice that from aluminum hydroxide to water, there's a 1 to 3 stoichiometry. So 1 to 3 stoichiometry for aluminum hydroxide to water. So what we do is we start out with the moles of aluminum hydroxide. We had 6.40996385 times 10 to the minus 3 moles of aluminum hydroxide. And you're going to get 3 moles of water formed for every 1 mole of aluminum hydroxide, which allows you to cancel moles of aluminum hydroxide. And your answer is that you're going to generate 1.92298916 times 10 to the negative 2 moles of H2O. Now, let's convert that to grams of H2O, which is a molar mass of 18.01528, so times 18.01528 grams per mole of H2O means you will get, after sig figs, you're going to get 0.346 grams of water. And that's your final answer for that part of the question. Now, if you were to add up all the different quantities that you get, you start off with 0.5 grams of aluminum hydroxide. This is part D, actually, that I'm doing, showing the law of conservation. And you ended up using using up 0.701 grams of hydrochloric acid in your stomach. You got 0.855 is the answer for the amount of aluminum chloride that's formed, and you get 0.346 for the amount of water. Now, if you add these two up, you get if you add up the amount of weight of these two things, it adds up to a total of 1.201. If you add up the total of these two, you also get 1.201. And that just proves the law of conservation of mass. The mass of the reactants has to equal the mass of the products. Of course, in real life reactions, you might not get 100% reaction. You might get stuff volatilizing, so you can't weigh that. It's going to disappear. It still exists. It's just hard to prove unless you have solid substances forming or aqueous substance, so that everything is still there after the reaction. So it can look like the law of conservation of mass is being violated, but in fact, it's everything that was in the reaction originally is still there. It just may have gone off into the atmosphere. For example, when you burn gasoline in your car, you may have 70 kilograms of gasoline in your gas tank, but when your gas tank is empty, where did it all go? Well, it got pumped through the engine and out through the exhaust. It's in the atmosphere in the form of CO2, water, soot, and whatever else your car belches out. Okay. Well, yeah, you wanna give an answer? Mama's meowing at me. Yeah. I agree. It's really boring, I know. Okay. 374. is the Alka-Seltzer question. It's this one's daunting. It's a whole page on my notebook. But you know what? I think you guys deserve it if you want it. So the question is this. The fizz produced when Alka-Seltzer tablets are dissolved in water is due to the reaction between sodium bicarbonate and HCO3. Hope you know your polyatomic ions by now. And they give you the formula of the citric acid, which is H3C6H5O7, aqueous. When the Alka-Seltzer tablet dissolves, you get 3 carbon dioxides, 3 water molecules, and sodium citrate as your products. So in a certain experiment, 1 gram of sodium bicarbonate and 1 gram of citric acid are allowed to react. A, which is the limiting reactant? B, how many grams of carbon dioxide form? C, how many grams of the excess reactant remain after the limiting reactant is completely consumed? Again, if you can solve this question, you're in a good place. It means you understood. Oh, you know what? I just read the wrong question, guys. I'm sorry about that. It's not the Alka-Seltzer. But you know what? Try that for homework. 373. I'll give you the solution tomorrow. All right? So try to do. You can do 373 for tomorrow. Mind you, I gave you the answers already. So let me see what you guys have in hand already before I start handing out prizes. Oh, you want to go see mommy? Here you go. Mama, go. You suit yourself. You want to go on the balcony? Go on the balcony. Here you go. Just going to plug my phone in. I don't want it to die. Okay. So, yeah, 374 for homework tonight. See how you do that. No, the Alka-Seltzer problem is 373. I'm going to do 374 now. All right? So 373 is for homework. And I don't know if you can post a picture of your answer. If you do that on my on this video, in the comments of this video, if you post 373, I'll reward you in some way. Okay, so we're going to try 374 now. Here's the question. One of the steps in the commercial process for converting ammonia to nitric acid is the conversion of ammonia to mononitrogen oxide, NO. In a certain experiment, 1.5 grams of ammonia reacts with 2.75 grams of oxygen. A, which is the limiting reactant? B, how many grams of NO and of H2O form? C, how many grams of the excess reactant remain after the limiting reactant is completely consumed? And D, show that your calculations in parts B and C are consistent with the law of conservation of mass. Just another reminder, I see there's 5 people online. I maybe had my back turned when you checked in, but if you haven't checked in by now, just write your name in the comments and send it to me so I know that you're there. It's nice to know who's watching. So the first step of this is to make sure that you have the balanced equation. This is called the Ostwald process, isn't it? So 374. So you have 4 ammonias plus 5O2 gas gives you 4NO, also a gas, plus 6H2O gas. Now you want to go see mommy. There you go. So, we start off with 1.5 grams of ammonia. We're going to divide by the molar mass of ammonia, which is composed of nitrogen, 14.0067, plus 3 times oxygen, 1.00794. Gives you 1.5 grams over 17.03052 grams per mole, which is 0.088007717 moles of ammonia. Do the same for the oxygen. Do that over here. 2.75 grams of oxygen with a molar mass of 15.394. Remember, oxygen is diatomic, so you multiply by 2 grams per mole. And you get 2.75 grams of oxygen divided by the molar mass of diatomic oxygen, which is 31.9988 grams per mole, equals 0.085940723 moles of O2. Now, the question is, which one of these things is going to finish first? The stoichiometric ratio is 4 to 5. That means that for every 4 moles of ammonia, you need 5 moles of oxygen. Just by looking at it quickly, there's fewer moles of oxygen. So even if it was, say, 4 to 4 or 5 to 5, if it was the same stoichiometric ratio, oxygen would finish first. But this reaction demands more oxygen than it demands ammonia. So just by inspection, I can tell the oxygen is going to finish faster because you have less moles of oxygen, but you need more moles of oxygen for the reaction to work. So you can see this by inspection if you just think it through. But if you don't like doing that, pick one of them and find out how much you need of the other one. And that'll tell you whether you have enough or not. And you'll find out right away which one the limiting reactant is. In this case, this is the limiting reactant. The oxygen is limiting reactant. So I'm going to start my calculation from the oxygen. So I start off with the moles of oxygen, which is this. And I know that I require 4 moles of NO. Sorry, they're asking us how much nitrogen monoxide is produced. So 4 moles of nitrogen monoxide is produced for every 5 moles of oxygen used. So that allows you to cancel moles of O2. So this times 4 divided 5 gives you the amount of moles of nitrogen monoxide you're going to get. What you're going to get is 6.875 257 821 times 10 to the minus 2 moles of NO. And then we're just going to find out the molar mass of nitrogen monoxide. We're going to multiply by the molar mass of nitrogen monoxide. So times the 14.0067 for the nitrogen plus the 15.394 for the oxygen grams per mole. What you get as an answer is, and I'll just cut to the chase. I'll give you what you get in sig fig with the proper sig fig. You get an answer of 2.06 grams of nitrogen monoxide as your final answer. They're also going to ask you for part 2 of part B, they're asking you how much water you're going to get in the reaction. The stoichiometry is 6 to 5. So again, you always start your calculation from your limiting reactant, because that's what's going to stop the reaction. So you again start from this number of moles, 0.0859, and now you're going to say 6 to 5 ratio, and the number of grams H2O you're going to get is, if you follow the same procedure, and I know you all have it in hand anyway, you have the calculation already, just check your answers. You're going to get 1.86 grams H2O. Okay? Now, in part C, it says, how many grams of the excess reactant remain after the limiting reactant is completely consumed? So let me make some room on the board for that. So all of the oxygen is going to be used up. So what you do is find how many moles of ammonia. The key of this equation, part C, is to find out how many moles of ammonia is used by combining with all of the available oxygen. So we start off with the moles of oxygen that we have. We have 0.0859 40723 moles of O2. Then we're going to use the stoichiometry. We know that 4 moles of ammonia is used for every 5 moles of oxygen. So times 4 moles of ammonia used for every 5 moles of oxygen used. Moles of O2 will cancel in this, and you'll get a value of 6.875 25784 times 10 to the minus 2 moles of ammonia is used. But you already have 0.088 moles of ammonia. So you take your original amount of moles of ammonia. This is what you had starting with. And you subtract this number, it's the amount that you're going to use in the reaction, which is basically 0.06875255784. What you're left with is 0.019. You'll notice I keep all the decimal places, because if you don't, you get it's easy to get rounding error. I'm being maybe a little bit excessive about it. You could probably cut it off at the 4th or 5th decimal place, you'd be okay. It won't be a problem. I just like to keep everything. So you have that many moles of ammonia left. Then you can just simply convert it to the grams of ammonia. We know that from previous calculations, the molar mass of ammonia is 17.03052 grams per mole. And that translates into 0.329 grams of ammonia. That would be your final answer for that part of the question. Now, if you were to add the reactants and products, you should get the same number. Now, I'm noticing here that I have some appears to be a contradiction in one of my answers, so you might want to check it. And of course, if you find that contradiction, I will give you a bonus mark. I'm going to conclude the class now, and so for your homework, you know what to do. It's question 375. No, sorry, question 373, the Alka-Seltzer question in your book. Do that for tomorrow morning, and if you get an answer to me, I will give you a bonus on the final exam of +1. Okay, if you do a good job, show all your work, and that'll count towards your mark. And hopefully we'll be back in class before too long. I foresee this is probably going to go till the end of, probably at least till the end of April. I want you to watch something interesting. There was a doctor by the name of Vladimir Zelenko, Zelenko, if I'm not mistaken, and he's come up with a protocol for apparently preventing people from dying. He gives three medicines to his patients. He gives something called hydroxychloroquine, which is an anti-malaria medication. Now, if you just use any one of these chemicals by themselves, it doesn't really help. You have to use them all three together. So hydroxychloroquine, zinc sulfate, and Zithromax. So the first one, hydroxychloroquine, is an anti-malarial medication. It's an ionophore, meaning it basically allows ions to go into the membrane. It helps ions pass through the membrane of bacteria and possibly also eukaryotic cells. I don't know for sure. But what it does is it potentiates, it makes more powerful the action of zinc. Apparently, zinc interferes with the replication of viruses. But if you just take zinc, not enough of it gets into your cells to actually protect you from the virus replicating inside your cells and hijacking your cellular machinery. So by combining the hydroxychloroquine with zinc, apparently it brings enough zinc into the cell to slow down the replication of the virus enough so that your body can build a proper immune response and kill it off before it kills you. Because what happens with the coronavirus is it gets into your lungs and it causes the massive cell death, and then your body's trying to clean up the mess, and it basically just fills your lungs with fluid, and that's what kills you. And if you're young, a lot of times your immune system is able to replicate fast enough to kill the virus, but with older people, the response is not fast enough. So what this procedure does is it buys time for the patient's immune system to save themselves. And the doctor was sort of joking with Rudy Giuliani in their interview on Facebook, which I watched last night. The patients still feel terrible, but they're still talking and they're still complaining about how they feel terrible. But the point is they survive. It doesn't kill them. And that's what we're looking for is that a treatment that is actually effective enough. And I think this doctor is doing a fantastic job. And he also there's a third thing he adds. He adds the Zithromax. Zithromax, also known as azithromycin, is a broad spectrum antibiotic. Now, when you're sick with a virus, it kind of weakens your immune system, so you become more susceptible to bacterial infections. So if you get a bacterial infection on top of your virus, it can kill you. So the Zithromax is just to prevent bacterial infections. So those three things together, apparently, the doctor says he's getting great success. I'm mystified at why the treatment is not being used. There are people coming on the internet saying, "Oh, it causes arrhythmia." So what? It causes arrhythmia. What if it kills 1 in 1,000? If it saves 50 out of 1,000, it's worth the risk. That's what it's all about. In medicine, you got to weigh the risks with the benefits and then take the best. So, guys, this is a great lesson for you to watch and see how there's science and then there's politics, and the two are always in a tug of war, and sometimes, unfortunately, the politics wins. Pray that the right thing gets done. Also pray for me not to get coronavirus, because apparently it hits Italians pretty hard. So we'll talk to you tomorrow, guys.